We pride ourselves in this conference to take the occasional left turn, if you will, into subject matter that might be considered to be a little bit non-traditional for a conference called Thinking Digital. The title of this section is called Disturbing the Universe. It's actually taken from a physicist named Freeman Dyson. It was a sort of autobiography. It was and is an awesome book. I'd recommend any of you to give it a try. And I've always had a great interest in physics. My one and only, I think I've given two wedding speeches, but the last one I gave was for a physicist getting married in, I think it was in 2005, or no, 2004. In it, I tried to compare the universal four forces and love and marriage. Yeah, one of the freakish things about physics, there's lots of freakish things about physics, I know that Tara will cover some of those, is there's this mystery about the four universal forces. You've got the strong force, the weak force, the electromagnetic force, and gravity. And they've kind of figured out, they've got relationships between the three of the forces, but gravity is one they can't figure out why gravity is so weak. And to give you an example, the weakest of the first three forces, the electromagnetic force, that's right, yeah? It's a weak force, sorry. That's probably the name probably gives it away, doesn't it? The weak force, yeah. If my arm was one unit of the weak force, my other arm, if it was gravity, would have to extend beyond the bounds of the known universe to be equivalent to this one arm length of the weak force. And so there's lots of interesting things that are going on there, and that's, I think, part of there's not been a bigger story in physics recently than obviously the Large Hadron Collider, which Tara has been working on. She's based normally at University of Liverpool, I should also add that she does a fair amount of work with the BBC and others to sort of help spread the education to a wider audience about physics and why we should care. So with that, I'm very happy to introduce her and welcome to our stage.
Thank you, Herb. Right, so now for something completely different. Thank you for that lead-in. So I want to talk to you about disturbing the universe from a completely different viewpoint. I want to tell you how in particle physics we not only disturb the universe, but we quite literally shake it to pieces to do our research, to find out what it's made of at its deepest levels, to find out how those parts knit together, and basically to find out how the whole thing ticks. So in the next 20 minutes or so, I'm going to take you on a really hectic tour of everything we know about the universe, the biggest questions and mysteries we have about it, and then importantly, how we're trying to find answers to those mysteries. Herb mentioned the Large Hadron Collider. Here's a picture of it, and I'm going to be telling you about that facility later on. So let me start at the beginning. And the aim of physics is, well, something very general and something very simple, just to understand the universe, why it's the way it is. And I've tried to summarize everything we know about the universe in one picture here. So on the left-hand side, we have the Big Bang, the moment of creation of the universe, where we had this tremendously energetic fireball of energy that created everything we see around us in the universe today. Now, that early universe looked very different to the universe we see around us now. There are no stars or planets. Instead, it was very, very hot, it was very, very dense, and matter stuff existed in its fundamental constituents, as fundamental particles, the ingredients of atoms. That's what the universe was at that very early time. As soon as the universe was made, it expanded rapidly, and as it expanded, it cooled. And as it cooled, at some stage, it became more energetically viable for everything in it to clump together into new forms. So after a few 100,000 years, we get the first atoms. After many, many, many millions, billions of years, we get stars, galaxies, and then here we are, right on the right-hand side, 14 billion years later. Well, that's what we think happened. How do we know it? Well, for the universe now, we can actually look at it with telescopes, and we can send out probes as well. But if we really want to understand how the universe evolved and got to where we are today, we also have to understand what went on right at the beginning, in the very early universe. And that's where particle physics comes in. Because in the particle physics experiments, we actually, literally, recreate those very energetic conditions that existed just after the Big Bang. And we do that because we want to study what everything is made of at this very deep level. If we can recreate those conditions, we recreate those ingredients of matter, and then we study them. That's the basic idea. So what do we know about the universe? I'll start off on the positive, optimistic note. So it's actually very, very simple. Everything we've seen seems to consist of no more than 12 ingredients, 12 fundamental parts of matter. And what sticks these parts of matter together to make everything that's familiar to us today are the small number of fundamental forces that Herb told you about. There's the weak force, the weakest force, affecting everything. This is the one that's responsible for radioactive decay. We have the electromagnetic force, most familiar to us in everyday life. It's powering the lights, it powers the laptop, everything. Very useful. And we have the strong force that keeps atomic nuclei together. And that's basically all we need for particle physics to explain what we see in our experiments. Now, of course, it's not the whole story, as Herb's already alluded to. There's one other force that's quite important to us. That's gravity. Keeps us stuck to the surface of the Earth and the Earth going around the sun. And for us, though, gravity is so much weaker than the other forces at the very tiny distance scales that we look at that we just ignore it. It plays no part in our theories at the moment. So we have matter and we have the forces that stick it together. And we even have a picture for how those forces work. So we think what happens to make a force work is that a force-carrying particle is exchanged between matter particles. And that's how the action of a force is felt. So that means that our universe is no more than a recipe made of these fundamental ingredients, our fundamental matter particles and a small number of particles that convey our forces. And we even have a theory that encapsulates this mathematically that we can use to predict what we see in our experiments. And this theory is really, really, really good. It's so good, actually, that we've never yet made an experimental measurement that disagrees with any of its predictions. This theory is so good that, hubristically, we call it the standard model of particle physics. Well, I would be giving a very short talk if that's all there were to it. And that's all very good. It's fine having a theory that can predict things, but the problem is, good though our theory is, it actually doesn't explain very much at all. And this is a real problem for us because in fundamental research, it's your aim to understand and explain the phenomena around you. We have a theory that's effective at best. So having told you the good news, now I want to move on to the biggest mysteries that keep us up at nights. If you're a particle physicist, the things that wake you up at 3 in the morning in a cold sweat, thinking, oh gosh, I wish I could solve it. We really do these things. I'm going to give you 3 examples of some of the biggest mysteries that you can get out there in particle physics. First one, very simple. First problem I want to tell you about concerns a very simple property of matter, and that's mass. We know about mass. We all have mass. We can see it when we stand on weighing scales. You know, there's a very obvious effect there. And we also know that our fundamental particles, our ingredients of atoms, also have mass because we can measure it in our experiments. That's fine. What we don't know, though, is why our particles have mass, what mechanism gives them that mass, and why they should have the particular values of mass that they do. And I've tried to allude to the different relative masses of these particles by the different sized blobs next to them. You'll have to excuse my physicist's artistic impression in this talk. I'm afraid we're not very high-tech at these things. So we don't understand mass. We don't understand why particles have different masses. And in particular, we don't understand why the mass of one particular particle, the top quark, is so much bigger than the others. A top quark, and this is incredible, has the same mass as an atom of gold. And yet it's at least 1,000 million times smaller than an atom. At least because it's so small that we've never been able to measure how big it is. It might be infinitely small for all we know. So problem number 1 concerns mass, a very simple quantity. We don't understand it. We'd like to. Now, we do have a theory, though, that tries to explain this. And it's not a new theory. It was first put forward in the 1960s by many people, amongst whom was a man called Peter Higgs. And this theory attempts to describe mass as a property that all stuff in the universe gets by means of its interaction with a new type of particle that exists throughout the universe. and the amount of mass a particle gets just depends on how strong that interaction is. So being unimaginative people, we've called this particle the Higgs particle. We've named it after Peter Higgs. Now, I should note here that occasionally you see this particle referred to as the God particle. This is thanks to a book that was written in the 1990s by Nobel Prize winner Leon Lederman. It's got no deep significance. Don't be taken in by the title. We all absolutely hate it. We'll refer to this as the Higgs from now on. So here's our theory that might explain this mystery. And in fact, this theory of mass forms an integral part of our standard model of particle physics in the universe. And in so doing, it's played its part in every successful prediction that's been verified by experiment. But it is just a theory. And it is just a theory because it's one experimental prediction. The existence of this elusive Higgs particle has never been proven. We have never seen a Higgs particle in any of our experiments, despite man-years of effort looking for it. This is what I mean by elusive. And this is our problem, because if we can't find a Higgs particle, we can't be sure that it exists. And if a Higgs particle doesn't exist, then our theory that explains mass is just wrong. And at that point, this problem becomes incredibly serious, because if that theory is wrong, our whole understanding of the universe, which is based on that theory, is also incorrect. Very incorrect. So incorrect, we'd have to throw it out and start from scratch all over again. So it's for that reason that this search for the Higgs particle assumes such prime importance amongst particle physicists. And we'll always talk about it whenever you come and see us and ask us questions. We always manage to slip it into conversation because it's always going on at this subconscious level. However, it's not the only problem that we're trying to solve. Here's another one, antimatter. Antimatter is really bizarre stuff. It's like the inverse, mirror version of normal matter, normal stuff. And the problem is basically that we don't seem to see any antimatter in the universe around us. Now, we know we don't see any antimatter because when antimatter and matter meet, they annihilate, releasing huge amounts of energy. So, for example, if I have a gram of antimatter, not a great amount, meeting a gram of normal matter, the annihilation has the explosive force of 20,000 tons of TNT. This is the sort of thing you would notice if it was going on around you. It clearly doesn't. We've not seen any evidence anywhere in the universe. But the problem is, we think that when the universe was created in the Big Bang, equal amounts of matter and antimatter were created. And this whole annihilation business was going on all the time in the very early universe. Matter and antimatter met, annihilated, giving you matter-antimatter particle pairs that went off, annihilated, and so on. And this whole battle continued as the universe expanded. But as it expanded, it also cooled. And as it cooled, these annihilations became less and less energetic, until eventually, maybe about a minute or so after the Big Bang, there was no longer enough energy in these annihilations to make new matter-antimatter particle pairs. And this whole cosmic battle between matter and antimatter just stopped at that point. And what we have in the universe now is a consequence of a very, very tiny imbalance, no more than 1 part in a billion, between the amount of matter and antimatter that was present there. Well, that's weird. We think that there has to be some really subtle difference in the behavior of antimatter and matter for that to happen, but we just don't know what. And we're trying to understand it because it's vital to understanding how the universe evolved to where we are today. Well, that's only 2 problems. The third problem is even bigger. And the third problem is just that although we seem to have described everything in our experiments, cosmologists tell us that's only 4% of the whole universe. 23% of the universe consists of something weird called dark matter, and 73% consists of something even worse called dark energy. Now, in particle physics, I want to come clean right now. We have no idea what dark energy is. It's a complete mystery. We also have no idea what dark matter is either, but at least we do have some theories that might explain what dark matter is made of. And those are theories that we can try and test in our experiments, although I have to say we haven't found any evidence to support that. Any of those theories yet. So those are just 3 mysteries. And to paraphrase Donald Rumsfeld, those are just the known unknowns, or at least a selection of the known unknowns. There is also the gravity that Herb mentioned. I've skirted that under the carpet. You know, there's an awful lot we don't know, and apart from all the unknown unknowns that are going to hit us when we find out more information about any of this. But finding answers is what we're about. It's what drives us forwards. It's what propels us to do our research into the unknown. So how do we find out answers? Well, if you're a particle physicist like me, an experimental particle physicist, you join a large particle physics facility. And I work at CERN, the European Centre for Particle Physics. This is one of the 2 or 3 centres in the world for trying to perform research to answer the questions I've just been telling you about. This was formed over 50 years ago. It's an international organisation. It really is. It's like the UN of particle physics. And particle physicists from all over the world collect together, come to this place to work together, to collaborate freely, openly, and on experiments designed to try and find the origin of mass, dark matter, you name it. We try and find any answers we can. Now, CERN is particularly exciting at the moment, and it's particularly exciting because of a new facility we've built there, the Large Hadron Collider, or LHC for short. This is, well, it's been billed in some circles as the world's largest piece of scientific equipment, the world's largest machine. Well, there's some debate over whether it actually is or not, but there's no doubting it is very large. What it is a 27-kilometre circular particle accelerator, atom smasher if you like, that's situated 100 metres beneath the ground on the French-Swiss border near Geneva. There's Lake Geneva here with the Alps in the background to try and give you some sense of context as to why particle physicists like to work out in Geneva, particularly if they're skiers. So if you go out to Geneva, of course, you don't see any evidence of the LHC on the ground surface. But if you can go 100 metres under the ground, and you can go and visit and walk around a little bit, you'll find that it looks like this. A long circular tunnel, not dissimilar in size to something like the London Underground, with a continuous chain of long blue magnets. And it's these magnets that form the heart of the particle accelerator. Because what goes on when the LHC operates is that 2 beams of protons, that's the nuclei of hydrogen atoms, are circulated in opposite directions around this ring. And it's the job of these magnets to accelerate them up to enormous energies. I mean, really, really enormous. They're accelerated until they're going at only 20 kilometers an hour less than the speed of light, for example. It's that fast. And then, when you've got them moving this fast, you smash these beams into each other at 4 points around this ring where we build up our experiments that take snapshots of what goes on. Now, the LHC really is amazing in so many aspects, not at least in terms of what we can do with it, but in terms of actually building it. It's quite amazingly large when you consider how small the particles are that we're trying to investigate with it. Actually making it was a civil engineering challenge, second only to boring out the Channel Tunnel. And as to the particle accelerator itself, well, it's reliant on these magnets. These magnets are superconducting. They operate at temperatures even colder than the outer space around the Earth because they use liquid helium as a coolant. They're incredibly, incredibly strong. And they need to be strong because our beams of protons have the stored energy of half a lightning bolt, of a high-speed train. They're things that you don't want to stand in front of, otherwise you get a large hole inside you. Not good for you. So what goes on when the LHC operates is that when these 2 beams collide, for a very tiny instance of time, in a tiny area of space, we actually recreate the very early universe, those conditions, which means we recreate the particles that were present there. And if we build an experiment around there, we can detect these particles and take the snapshot, essentially a 3D digital snapshot of what goes on. And these experiments, too, are large, complicated devices. I've shown you here on the left an example of the Atlas detector. You might have seen it before because it was in a lot of publicity around startup last year. Atlas is notable because it's so large. It's 20 meters tall. It's the size of a 5-story building, the size of a cathedral, 100 meters underground. And it's not just large in extent either. There are over 2,000 particle physicists from all over the world that work on this experiment. It's a huge collaboration of people to work together. And yet you need this many people to design and build an experiment like Atlas because it's so huge and complicated and expensive, and also to analyze the data that it produces. Now, of course, Atlas doesn't look like this anymore. This picture was taken whilst it was under construction. If you could see it now, this entire volume has been filled with precision particle detectors whose job it is to do the capturing of imaging when these particle collisions take place. And these particle detectors range in size from the very tiny around the collision point. This is a picture of a silicon-based detector And this silicon part here, the semicircle, you could hold in the palm of your hand. I like this one. It's from my experiment, the LHCb experiment, and we built this at Liverpool, so I'm strongly advocating it. But it's a wonderful detector, because what it can do is it can tell you precisely where something has gone through it. So precisely, it can tell you the position to within 1/10 of the thickness of your hair. It's that good. And it's that level of precision that we need to do some of our physics, particularly to understand antimatter. However, not all detectors are that size. By the time you get out to the very outside of our experiments, it's very large. And the outer layer of particle detection, is absolutely massive. This is a picture of the last layer in the Atlas detector. Note that if you're a particle physicist, you need a crane to work on this experiment. A good head for heights is essential in particle physics. These are massive. And that's just to give you a sense of scale for how we operate our facilities. So to recap then, it's the LHC that recreates the very early universe, the experiments that take the snapshot. If we record a series of millions of these snapshots, analyze them offline, then we can start to build up a much bigger picture of what went on in the early universe, and particularly how things interacted together that might solve our mysteries. This is the angle that we take. So, having built this equipment and hopefully having it running by the end of this year, how are we going to make progress in answering the questions I've told you about? Well, I'd just like to discuss this briefly now for the rest of my talk. I want to go back to the first question I told you about, the origin of mass, our search for the elusive Higgs particle. Now, we're not hunting in the dark for this thing. We have quite a good idea what we're looking for, because we have a theory, and that's key to it. Because we have a theory that describes the behavior of this particle, that means we can simulate what we expect it to do inside the LHC and inside our experiments. That means we can simulate what we expect it to do in any one of our proton collisions. And this is a picture of a simulated proton-proton collision where a Higgs has been produced. And what's happened is that it hasn't hung around, it's decayed almost immediately to these particles represented by the 4 green lines. Now, digging out that signature of the Higgs from all this other mess that goes on when protons smash into each other is straightforward enough. We can cope with that. It's just a pattern recognition problem that's not difficult. And if our theories are correct, then we'd expect this sort of process to go on once every hour or two when the LHC is running. So this sounds very positive in terms of making progress in our whole understanding of the universe. Well, unfortunately, it's not that easy. If only it were, we would have discovered it by now. And the problem is, we're looking for something that's produced every hour or two amongst 40 million other things going on every second. The LHC delivers collisions 40 million times a second. And our problem has rapidly multiplied in complexity. We have a huge selectivity problem. It's like finding a person in 1,000 world populations, or if you want to be a bit more artistic and poetic and less scientific about it, a needle in not just 1 but 20 million haystacks. Quite a job. Quite a job in terms of data manipulation, because if you want to store any one of these proton collisions, then to read out a detector like Atlas means you have to read out at least 100 million, or 100, yeah, that's right, 100 million electronic channels of information. It's a lot of data to manipulate. And we're talking typically, to perform a search like this, hundreds, thousands of terabytes, if not petabytes of data. It's a lot. So much that we come up with these crazy pictures to try and illustrate it. If you were mad enough to write out this data onto CDs, you would indeed get a very large pile of them that was 20 kilometers high. We don't. We store it much more efficiently. But we have worked out, if we're going to analyze this much data, and this is the challenge we need to overcome to make progress, we're going to need about 100,000 computers to do it. And that is a problem in pure research, because if you're a physicist, no government is going to give you 100,000 computers. No country is going to give you 100,000 computers. If we're going to cope with this final challenge, we need a new computing paradigm. And CERN computing scientists have done that. It's called the grid, and it's like the next step up from the World Wide Web. In fact, it's very similar to the cloud that we heard about first of all, except this is our homegrown version that I'm almost embarrassed to tell you about, because it's bound to be far less sort of, well, high-tech. The grid, as I said, is the next step up from the web. So whereas the web was invented at at CERN as a way to allow particle physicists to share their information with each other in the 1990s. What the grid will do is allow us to share not just our information and our data, but also our computing resources as well. Our data storage facilities, our CPU farms, our processors, we just stick it all together. And if we can do this with a layer of middleware, a layer of software that makes that change transparent, then because we have so many particle physicists from all over the world collaborating together, if they all make their computers available to this facility, we can actually make a geographically distributed supercomputer that's powerful enough to actually analyze all this much data. That's what the grid is. And in fact, the grid does exist already. This is a map of grid world. Everywhere you see a blob, that's where you have a particle physics institution that's already connected its computers to the grid. Everywhere where you see a line, this is where a particle physicist has written an algorithm, a piece of software that's traveling this computer, looking for data or sending back results. And we know that this grid works because we've already used it. We've done dry runs to cope with the amount of data we expect to get from our experiment. And it's not just us that find it useful. Because we've had spare time on the grid, we've let other people with computationally intensive problems use it too. So it's already been used, for example, to search for drugs to combat malaria and so forth. So the grid is the final piece in our armory, our toolbox, to allow us to investigate these big mysteries of life. So I want to just finish this very brief and hectic tour, having told you what we understand, what we don't understand, what we're trying to find out, how we're trying to find out about it, with just a forward look as to where we might be in 10 or 20 years' time. And I am a particle physicist. I do blue skies research, and this is why I put the question mark on the screen. Because the big deal about blue skies research is that we don't know where we're going. The fantastic thing about the Large Hadron Collider in particle physics is that we have no idea what we're going to find. Quite literally, we have never, ever looked at the universe when it was this young before. The LHC is going to recreate conditions in the universe when it was only a billionth of a second old. We've never looked at it when it was at such early times. And that's why this is such a fantastically exciting voyage to go on, a voyage of discovery. So we don't know what we're going to find. We really hope we're going to make some headway with understanding the universe and the way it all sticks together, but we don't know. We may just come up with more problems, more mysteries. 30 or 40 years down the line, we may come up with spin-off technologies that benefit mankind, much as previous accelerators and detectors have provided technology for medical scanners and so on. But we don't know. This is why it's such a delightful and exciting and slightly nerve-wracking deal to be involved with. So I don't know if that's an optimistic note to finish on or not, but all I can say is we all have to wait to see what happens. That's what research does for you. So that's my final word. Thank you.
We are running pretty late over time here, so I'm going to just see if is there a single quick question? Anyone out there that wants to say anything? Right. Oh, sorry, Tony.
All right, so if you were to take a particle accelerator and you would smash two atoms together. Now let's say that all of a sudden on one side there were no particles. Would that lead into proving that there's more dimensions that we previously thought?
Well, that is actually one of the more exciting areas of research going on. To come back to Herb's point about gravity, I mentioned that we ignore gravity in our theories, and it's true that it doesn't make much difference to our answers, but we mainly ignore it because we don't know how to deal with it mathematically. Can't make it occupy the same equations as everything else. The only way we seem to be able to do that is to move to string theory, where we have extra dimensions of space and time. And research here has led, in some esoteric versions of the theory, to predictions that we can test at our colliders. So I know this sounds stupid, but if you have extra dimensions of space and time that are far enough apart, we can actually detect that influence on the collisions that are being made at the LHC. And people are actually searching for evidence of these extra dimensions at current experiments, and they're planning their strategies for doing it at the LHC. So the experimental signature that we would see is slightly different. It's not that particles would disappear into an alternate dimension or anything like that. What we'd see would be some some ripple that would manifest itself in our dimension as a massive particle that would, we always think of things in terms of particles. I think it maybe is a failing of our reasoning, but it's how everything seems to manifest itself to us. So these extra dimensions would look like a big, heavy particle being produced inside our experiment. And we have theories that predict how these would behave, what they would decay to, how we would find them. So we are geared up to actually looking for evidence of this stuff too.
Great. I have to end it there, I'm afraid. Okay. Thank you again. Cheers.
Thanks, Herb.
We pride ourselves in this conference to take the occasional left turn, if you will, into subject matter that might be considered to be a little bit non-traditional for a conference called Thinking Digital. The title of this section is called Disturbing the Universe. It's actually taken from a physicist named Freeman Dyson. It was a sort of autobiography. It was and is an
research to find out what it's made of at its deepest levels, to find out how those parts knit together, and basically to find out how the whole thing ticks. So in the next 20 minutes or so, I'm going to take you on a really hectic tour of everything we know about the universe, the biggest questions and mysteries we have about it, and then importantly, how we're trying to find answers to those mysteries. Herb mentioned the Large Hadron Collider. Here's a picture of it, and I'm going to be telling you about that facility later on. So let me start at the beginning. And the aim of physics is, well, something very general and something very simple, just to understand the universe, why it's the way it is. And I've tried to summarize everything we know about the universe in one...
she's based normally at University of Liverpool. I should also add that she does a fair amount of work with the BBC and others to sort of help spread the education to a wider audience about physics and why we should care. So with that, I'm very happy to introduce her and welcome to our stage.
Thank you, Herb. Right, so now for something completely different. Thank you for that lead-in. So I want to talk to you about disturbing the universe from a completely different viewpoint. I want to tell you how in particle physics we not only disturb the universe, but we quite literally shake it to pieces to do our research.
They've got relationships between the three of the forces, but gravity is one they can't figure out why gravity is so weak. And to give you an example, the weakest of the first three forces, the electromagnetic force, that's right, yeah? It's a weak force, sorry. That's probably, the name is probably gives it away, doesn't it? The weak force, yeah. If my arm was one unit of the weak force, my other arm, if it was gravity, would have to extend beyond the bounds of the known universe to be equivalent to this one arm length of the weak force. And so there's lots of interesting things that are going on there. And that's, I think, part of there's not been a bigger story in physics recently than obviously the Large Hadron Collider, which Tara has been working on. Awesome book. I'd recommend any of you to give it a try. And I've always had a great interest in physics. My one and only, I think I've given two wedding speeches, but the last one I gave was for a physicist getting married in, I think it was in 2005, or no, 2004. In it, I tried to compare the universal four forces and love and marriage. One of the freakish things about physics, there's lots of freakish things about physics, I know that Tara will cover some of those, is there's this mystery about the four universal forces. You've got the strong force, the weak force, the electromagnetic force, and gravity. And they've kind of figured out